So, when I try to start streaming,
Got it. Okay, thank you.
what does this mean?
So there's nothing to talk about.
No, it's a hard thing to answer.
My mind doesn't work that way for some reason.
Yeah.
It's
Well,
not touch
yeah,
even.
I mean, I'm using the same method I was confused why it works.
Good to be nice to have to point out that this is actually.
Oh, thank
Does
you.
it point out something about like memorization of full loss or something like that? So which one is that?
It's the neural net. Two-way one.
Two words. Adding a note about that for future generations.
Yeah, right. Yeah. Maybe you teach the class the second time.
That's right. Yeah, so it does say it doesn't compartment and regularization.
Right, and so yeah, it's the
But we all know
I see. Yeah, it was just kind of hard to see it
yeah, we must not do I think it's like the continuous. Anyone have questions on homework before class starts? A couple have already come up. Assume others would come up if they haven't, but.
So I was like wondering, for the regularization, should we use like half or not? So like half times W cross W.
So like it doesn't matter in the end
Yeah, it doesn't matter.
because you're adding it with like you. So in general, it doesn't matter because you typically add it with a hyperparameter specifying like its weight with the other losses, right? Like you're adding everything together, and you
Divide.
and you multiply by this thing. So it like in general doesn't matter because like whatever constant you put out there in front, it would get absorbed by the hyperparameter, right? The reason why it's usually formulated with a half is just because like the L2 norm, when you take a derivative,
Yeah.
2 cancels with half. It's just like a convenience thing. So it's like that thing that, like when you first took calculus and like they showed you that, it's like the answers were like that. Like, how did you get those? The teacher knew it beforehand what the answer was going to be. But yeah, and like in these problems, let's see. I can't remember. How do I have it go? Do I have it? In these, so there is so in all of them there is a weight, right? Like there's a regularization weight. Yeah. So it doesn't matter if what you do. It's just between two people, you get the same. Like if one used half, one didn't, you get the same solution, but for like one would get the same loss values and things like that. Twice the regularization value than the other person, right? So if you include a half, if person A includes a half and person B does not, then you get the same loss for different regularization values. The same loss when like person A has twice the regularization value as person. Does that make sense? Yeah. So it's just like one of those convenience things that you don't want to have a constant out in front of the ingredients, but it doesn't change things. Okay. Any other questions before we start? No? All right. So homework is due tomorrow. Uh-huh.
How do we turn in the homework?
Just upload them to the Canvas. That will be like the timestamp for when it's turned in. So in a Jupyter notebook, when you do all the work and then like you save it and download it, all of the output values are there still. So make sure if you don't download it and download it from Collaboratory and then upload it to Canvas without there being all the output. Okay. Let's get started then. So in the syllabus, can you tell if that's on over there? There's a green light. I'm not sure that's part of it. There we go. Okay, so in the syllabus, today was going to be on like how to use TensorFlow and how to write code in one of these frameworks. And what I have decided to do is to save that for next Thursday because I won't be here next Thursday. And Alessandro, who knows a bunch about TensorFlow, will give that lecture on like how to use TensorFlow, how to write things. So instead, what we're going to do is we're going to start into the history lesson today on convolutional networks. And part of today, it's a history lesson, but like along the way, we're going to see techniques that we use, and I'm going to spend some time kind of explaining those techniques. Things like regulation techniques like dropout and some initialization ideas. There's going to be 2 lectures on this, so we're going to get hopefully halfway through the history I got prepared and do the rest on Tuesday. There's a ton to learn here, mainly because like the stuff that people do now is really shaped by the networks that we'll be looking at today. And yeah, I mean, like I've said many times, like it's a really an empirical practice. There's not tons of theory guiding like what should be done, and the way that these empirical things get decided is basically through performing well on accepted like tasks or competitions. Usually, is where the tasks are decided, and yearly people make submissions, and then whoever wins that goes on to fame and fortune. And everybody starts using their architectures. And so anyways, we're going to start going through this today. It should be hopefully very useful in terms of like just understanding where we are today in terms of convolutional networks, like just how we got here, and probably won't indicate anything about what's going to happen in the future. Someone will come up with something else that's even better maybe, but hopefully it'll give you some understanding of like why, in each case, what the networks, how the networks change to get like better than the previous generation. So anyways, let's get started. So this I think this has been mentioned before in class, but this is considered like the first really like successful use of the convolutional networks. 1998, when this paper was published. Kuhn and Bengio are both authors on this. There's a couple others, but yeah, this is like the first kind of modern convolutional network, I guess. And it's modern because it kind of looks like the things that we talked about last time. So this is the architecture. This was actually trained on MNIST. Now, MNIST is something I think we've mentioned a couple times, where it's just like it's little the images actually. It's funny because anyways, they're not usually 32 by 32, but here they're 32 by 32. But anyways, they're small images that are basically just like a single handwritten digit from 0 to 9. And it was actually made from existing data sets from NIST, the National Institute of Standards and Technology. They had a bunch of these handwritten data sets, digit data sets. The authors of this paper put them together into what they call modified NIST, which is now MNIST. And this is where it comes from, 1998. And like, models are still trained on this as a way of kind of exploring different ideas, although it's starting to go away as there's more power to work with more powerful networks. But it's pretty basic. You have convolutional filters. In this case, they were 5 by 5. The filter sizes were 5 by 5. A stride of 1, so just moving around up, left and right, up and down by 1 pixel. And there was this interplay between, there was interleaving of convolutions, and then what they called in the paper subsampling layers, but what we now call pooling layers. And they were 2 by 2 stride 2, so there was no overlap in the pools. And so it was 5 by 5 convolution, 2 by 2 stride 2 pooling, another 5 by 5, then another pooling, and finally a 5 by 5 that's called a fully connected layer. And it's funny because this is actually like it's a matrix, but it's called fully connected because these are if you follow all the dimensions as you go, the feature maps, activation maps, go from 32 by 32 to 28 by 28, then get halved because of the pooling layer, and then 5 by 5 gets you to 10 by 10, and then pooling again 5 by 5. So when it gets to here, it's 5 by 5. So when you do a 5 by 5, if you have a 5 by 5 filter with a 5 by 5 input of this layer, you just get one number. So it's thought of as like it's actually, these convolutions were actually fully connected from here to here. Yeah.
Does pooling have any benefit other than just reducing the complexity of the computation?
Yeah, it sort of it makes it has the effect of making the representations that it's finally learning sort of a bit invariant to where this digit exists on within this grid. You see, like if you think about, they didn't use max pooling here. Actually, it's interesting. These subsampling layers had some learnable parameters for like how you average the numbers and the 4 numbers in the 2 by 2 pool together. We usually do max pooling at this point, but if you think about what max pooling is doing, it's just saying, okay, like, what's the thing most activated in this grid, and if you're pulling those things together, especially over multiple layers of convolutions, then what you're saying is like, I'm looking for a certain kind of feature that is not necessarily like just in this like top pixel or over here, but sort of in this area. So it does provide some sort of invariance in that respect. But it also has the nice feature of totally reducing complexity by factors of 4 here if you stride in this way. But anyways, pretty simple. They set a baseline for everybody else to follow. Everybody else compares themselves on MNIST to this, and then later on to the best models. But this is kind of where it all starts. So it has a lot of these. So all of the convolution numbers we'll look at will all kind of have something like this. They'll be definitely adding a lot, and in particular adding depth. But this is kind of thought of as like the first one of all these. That was trained on MNIST, and like a lot of progress didn't really happen until this data set was put together, called ImageNet. And it's a pretty massive data set. in total, there's like, as I said, there's approximately 14 million images in this data set, and they're labeled, and there's approximately 20,000 classes. And the way they did the labeling, well, first of all, they just sort of scraped the internet. I don't really know how that happened, but they were sort of like, scraped the internet for whatever images you could find. And then, using Mechanical Turk on Amazon, they just had people label them. So that was a really intensive, costly process. And yet, what it did was produce a data set that then could be used to sort of benchmark how well we were doing on certain tasks. And so, what the what's the group's called? Pascal Visual Object. It's Pavlov. I can't think of what it all stands for. But anyway, some group then created this challenge that well, it's actually it's a group of challenges called ImageNet Large Scale Visual Recognition Challenge. There's a number of like tasks within it. The most popular being like the classification task. And what they did is they took this data set, took roughly about a tenth of it, 1.2 million images. There's 1.2 million training images. There's 50,000 validation images and 100,000 test images. Each of which has exactly one of 1,000 classes. So classes like breeds of dogs and different types of objects and person and things like that. So a lot of examples that we've seen. And they created this challenge. And it started in 2010, and you make submissions at the beginning of the year, and then the winners were announced at CVPR, which is held in the summer, usually in June. Actually, it was held this year here in Salt Lake City. Can anybody go to it? Go to CVPR? No. Anyway, well, you go next time, I guess. Let's see. Anyways, so this is what happened. And in 2010, people were doing some convolutional networks, but it wasn't, like, you look at some of those and you say, like, there's no way a convolutional network can work on this because it's, like, too computationally expensive and whatever. But it turns out that 2 years after the introduction of this challenge, you had two submissions that this is shallow. These really weren't convolutional. Well, these definitely weren't convolutional networks. But there was like manual feature extraction, and then you had some sort of shallow machine learning algorithm that was trained on it to predict these 1,000 classes from the images. But 2 years into the competition, you have the first convolutional network that wins this, and it wins by a ton. I was trying to come up with these numbers in my head last time, but here they are. In 2011, what you have is the numbers you're seeing here are top 5 error rate on the test set. So top 5 error rate is the fraction of images in the test set that where the correct class doesn't appear in the top 5 predictions. So your algorithm predicts, probability for all the classes. You take the top 5 of those. The top 5 error rate is the fraction that does not appear, the fraction of images where its class doesn't appear in the top 5 predictions, your highest probabilities. So that's how this is like, this particular task, the classification task, is evaluated. And they, basically, this group had it's not quite half, but it was a dramatic thing. And it was convolutional networks, and everybody was super surprised. And basically, it started this is, in some ways, you can think of this as like the beginning, the like AI revolution, and it was a big deal that this happened. And then you go to the next year, and like a huge gain or a reduction in the top 5 error rate, and then a huge reduction again. In 2014, this is actually the winner in the classification task, but 2 very different convolutional networks came in pretty close to each other. And then like huge again, big gain in 2015. And I remember this, when this came out, this was such a huge deal because
this was the first time when we were doing, when these convolutional networks were doing better than humans do on this task. So humans have a top 5 error rate of 5% roughly, and here this is doing 3.6, and you can see as the years have gone on, these two networks are sort of like modifications of this original ResNet, and yeah.
If human cannot recognize the image, how are they labeled?
Yeah, they're labeled by humans, so it's a good question. They're just tested on other humans. So you can think of it as like sort of just like the error that exists in this. So I don't know for sure exactly how it was done, but there were multiple people, humans, labeling each of the images. You get a lot of people labeling them, and then there would be a consensus on that. That would be the label. And then if you hand this to somebody else who gets to do it once, and you calculate their error rate on it, and you average it all together, then you get like roughly 5%. So it's a good question, and yeah, there's like a metaphysical sort of philosophical question there, like how do we know when AI is getting really smart? Because the only thing we'll have to evaluate it with is our own intelligence, and we won't be able to evaluate other types of intelligence possibly. What's really shocking about this too is that in not too many years we go from like 8 layers, which seems shallow now, but it was huge back then, to the winners of these more recent competitions that had a ton of layers, 152 layers. And yeah, huge progress has been made beginning in 2012. And so we're going to start going through what these are and a bit about how the progress was made. Okay, so the first one there is this AlexNet, the 2012 winner. This is that picture we talked about where if you go to the original paper, the top of this network is chopped off for some reason. And it was never reprinted with the full image, so AlexNet is famous because it wins this, it's the first convolutional network to win this competition, and the only picture we have of it is this chopped up. And so that's the one thing to show. So it has an architecture very similar to like LayNet in the sense of you have convolutions and then max pools. You actually have this this layer. It's a normalization layer that's not used anymore, but it was in there. Anyways, it's there. But you have this convolution max pool, and a bunch of convolutions, and another max pool, and then a bunch of fully connected layers. So this looks a lot like a LayNet. It's just deeper. And the question, like how do they make it deeper? Well, they were able to train on GPUs. Actually, they were able to train on 2 GPUs, which was a huge innovation back then. And the reason why this AlexNet is chopped in, so there's 2 chops. One is the unfortunate chopping of the image. But you notice how, like, here in this first set of feature maps, there's actually like 2 tensors, one on top of the other, right? Yeah. And I have some slides here a little bit that kind of point out what's happening here. But what they did was to have a bigger network, they basically like had the architecture sort of distributed across these 2 GPUs, and they sometimes, like the information that was held in them sometimes was communicated across at a layer, but in other layers it was not. We don't do things like this anymore, but it was like a big innovation that allowed them to gain a couple of percentage points to, I guess, reduction in the top 5 test error. But yeah, it was magical when it came out. So let's think about this for a second. Let's apply what we learned last time. So input to these 227 by 227 by 3. So the 227 is the images. Sort of a standard thing to do in ImageNet is to have these scale to 224 by 224. I think the 224 is that's like the shortest edge length of all the images in ImageNet. I think that's the case. I'm actually not quite sure on that. The 227 part is about like having it for doing convolutions, but in this first layer, the way that this was set up is that they had filters that were size 11 by 11, and they used a stride of 4. Now you remember from last time, no one ever uses 11 by 11 anymore, and no one ever uses a 4 by 4 stride because the filters are so much smaller. But nevertheless, this is what was done in the first case. And there were 96 of them, 48 in GPU 1, 48 in GPU 2. So what was the total output volume of this? You get some of the hard math already done for you. 227 minus 11 divided by 4 plus 1 is 55. So what is the what's like the size of the tensor for the future maps? Somebody go for it.
55 by 55.
Yeah, exactly. And so how many parameters is that? That's like, can't have to do that. But I shouldn't say approximately, I should say equals 34,848. So remember how this works. You have your filters, each one is 11 by 11, so there's 121 weights in that. There are 3 channels. Oh yeah, I failed to mention this. These are RGB images, so we're going to have 3 channels. And there are 96 of them. So you just do that multiplication, you have nearly 35,000 parameters in that first convolutional layer. Okay, now we have 55 by 55 by 96. That's the input to the max pooling. We do a max pooling. Here in this first max pooling, we have a 3 by 3 filter that's applied at stride 2. So what's the output volume? You have number 27 given to you there. So what is it? 27 by 27 by
55.
Not 55. The number of channels we have in the tensor. 96. Good. And how many parameters are in this? This max pooling layer. How many parameters do you need to determine the maximum in the 3 by 3 pools?
3 by 3 by.
No parameters.
Oh yes.
You don't need any. Yeah, you don't need any to decide what the maximum is. So 0 parameters. So yeah, those are good. Computationally, it's a very inexpensive way of reducing the spatial dimensions. Okay, so and so on. And here you go. You can take a look at these. So lots and lots and lots of parameters. Notice that these eventually go to a fully connected layer, and these happen to be 3 of them. So they chose to go from the outputs of this max pooling, so the feature maps here to that 2048. And the way that works is you just flatten this out. You just, like whatever the output is here, it's a tensor. You just flatten it out, and you do a fully connected layer of that flattened out tensor with the 40 on 96. And it doesn't really matter how you flatten it out. It's just going to learn how to, as long as you flatten it out the same way in all your iterations, then you'll be fine. If you don't do that, it seems that would be pretty bad. And anyways, so there's 2 of these, 40, 96 fully connected layers, and then there's finally this, the final fully connected layer. It's got 1,000 neurons. It's got 1,000 units. Why is it 1,000?
1,000 classes.
There's 1,000 classes. So this is where we apply our loss function to determine if we are making the correct prediction. Good. Yeah.
Did we talk about the normalization layers last class?
No, we didn't. We didn't, and we're not talking about this time because they're thinking of the past. What they were, the name of them are these: local response normalization, and what they were was it was a way of like creating local inhibitory connections so that like you enhanced like what was in the center of the field of view of the activation. So it would look at things nearby. It would normalize by their activations. So it was sort of modeled after some, like loosely after some of the biology in the human visual system. And what happens is in 2014, when BGG has a nearly witness, they get the second place submission. They just flatly state, like they show it in the paper, like, yeah, Norm didn't help when we did these kinds of networks, these local response normalization networks. And basically, no one ever used them
Not shown to help at all.
They probably help at sometimes, but they're just expensive to compute, and yeah, these things they just sort of drop out of. It's like you're reading a book, like somebody's writing a story, you're they're like 2 pages ahead of you. You're reading the book as you try to catch up, and then someone just says, decides in the story that like, yeah, these layers aren't good anymore. And basically, everybody believes it. It doesn't mean you can't use these. It's just that like a lot of people don't want to spend a lot of time on like looking for optimal architecture. They want to comment something that they know is going to be really great, and maybe make a few tweaks, but not like big tweaks, like introduce new types of layers. And that happens every once in a while, but it's usually from a grad student at university or something like that, not somebody working in the industry or something like that. Okay, so let's talk about what's cool about AlexNet. So besides it winning by a ton, it was the first like major use of rectified linear units. So ReLUs. Up until this point, basically you'd see sigmoidal types of activations, and ReLUs predated this by a couple of years for sure. But this was showing that it was really useful to use. In the paper they show that basically that the number of iterations that they needed to converge was they needed like an 1/8 less iteration. Like it really sped up conversion. You kind of saw this that day that we were playing around with the TensorFlow playground. Yeah, they use these local response normalization layers, not used anymore. And then they did this thing called data augmentation. And I'm going to spend a little bit of time right now talking about data augmentation because it's very useful, especially for ImageNet, and it might be useful for anything you might decide to do. So we've talked about regularization, and we've mostly talked about it as, and like in your homework, there is an additional loss term that you add to the data loss that is some sort of it's causing your weights to be configured in a certain way. So L2 makes them smaller. L1 tends to make them sparse, meaning there's lots of zeros, and you can combine them in any way you want to get both types of things. But there's other kinds of regularization, and always, again, regularization, when we talk about regularization, we're talking about a method or technique that is allowing us to generalize better away from the training data, when we go out of the training data. So, like improving our scores on the test data that we haven't seen, so this out-of-sample data. So data augmentation. So the way we've been talking about these things typically is we're given a load of data with some labels, and we just take those as they come, we run them through our neural network, compute losses, and we say, we can say something about how well we did. But data augmentation says, let's take these original images, and then let's just transform them in all kinds of ways that sort of make sense, and then use that transformed image with that same label, and use that as a new data point for training. This is like a super, super, super useful technique, especially on these data sets like ImageNet, where you can expect there to be lots of variation in the images, like illumination differences, coloring differences, orientation differences, all these different things. It's still a cat in that picture, and if your models can see examples of these other kinds of cats, then it should be able to generalize better to images it hasn't seen before. So a really common, easy thing to do in a natural scene is to just do a horizontal flip. So this is super easy to do, when your data is digitized, right? You just think about your arrays and you just reorder the arrays. Horizontal flips are in these natural scenes, like an ImageNet is a really common thing. Vertical flips are not. Why not? We don't see upside down cats on. Now, you could train it to recognize upside down cat, no big deal. But it's sort of like a waste of capacity in your network because your test set's not going to have any upside down cats. Now, if your test set was going to have some upside down cats, you better have some upside down cats in your training set. But because these are natural scenes, we don't expect to see many upside down cats. Of course, cats do all kinds of awful things, so maybe they are upside down. But like cars, we really shouldn't see upside down cars. We shouldn't see upside down trees. We shouldn't see upside down lots of things. So horizontal flips are very common, or like essentials for natural scenes, but not vertical flips. Also, something that's done very commonly, it was done for training AlexNet, is to randomly crop the image. So what was done for AlexNet is to basically take whatever image there was, rescale it so that the shorter side, whether it was the width or the height, whatever was the shorter side, rescale that to 256, and then randomly sample patches of 224. And so now what you're seeing is just like, lots of subsampled images of the same cat. So it's learning to see this at, it's not at different scales, and oh, shoot, I meant to pull out and scales. There are networks further down that actually do a lot of rescaling, but in this one they just did cross. But anyways, you can see how this might be a nice way of augmenting as well. I mean, even if you get this portion of the cat down here without the head, it's still a cat. And it would be good if your network could sort of recognize a cat without having to see its pointed ears and its awful eyes and things like that. At test time, what they also did to get their best networks was having trained it to recognize these 24 by 24 random samples. They actually did the same rescaling of the image, and then they took the 5 crops, the 224 crops that anchored at the 4 corners, and then the one right in the center. And then they classified all of those, and what they did was they took the softmax, so they ran it through the network, which is a process called inference. And yes, it would classify, but what it is, they took the softmax output, and they took it from the 5 crops, and then they did the horizontal reflection, so they actually had 10 crops, 10 patches. They got the softmax output for all of those, and they averaged those together. And then took the maximum probability within that averaged distribution and said that was the correct label. And that actually improved their ability to classify by quite a bit. There's lots of other things that you could do. This is another example that they did in AlexNet, was to randomize the contrast and brightness. What they actually did in AlexNet is pretty clever, actually, is they applied PCA, so principal component analysis, to the images, and they took the first 3 principal components, which were typically correlated with things like contrast and brightness, because these are things that vary the most, or the most common variations amongst all the images. And they just sort of like randomly added scaled values of those principal components to the image. So you get, something that, in this case, is a bit more saturated. And then that was also a form of augmentation that they tried out. So, yeah, maybe not something you think of first off, but if all you do is train these models and think about vision tasks, maybe you do that.
What is a PCA on an image?
Well, so it's a matrix, right? So they do this for each of the channels.
So PC generally gives us a set of like dimensions, right? From large.
Yeah. So okay, right. So you have a matrix. So if you just focus on one of the color channels, you have a matrix, and you can apply PCA to that matrix, right? So you're computing the principal components of that matrix. So a matrix you can think of as a map, a linear map, right? And what the principal components are, or more generally, that's the singular value composition. You can think of them as the axes along which, like the best way to think about it is you have your map that takes your sphere in however many dimensions, and it maps it to some sort of ellipsoid in the range of that matrix. And all that PCA is doing, or SVD more generally, is just saying, okay, what's the component with the largest axis in this ellipsoid? That's your principal component. Then it looks in the orthogonal complement of that, and it says, okay, what's the next largest one, and so forth. And those are your principal components. So it's the axes of most variation as determined by this linear map.
So I get another image after doing PC on one image.
No, so PCA gives you some vectors to deal with, and now you can just take however many of those you want, and you can create a low rank matrix out of how many components you have. So if you take, in this case, it took 3, like the 3 top components. You can create a low rank matrix out of those, and you can add that back into the image.
So they're being pretty thoughtful about this. Could I just take like 1,000 filters from Adobe Photoshop and like multiply my data set by 1,000?
Yeah, that would be really slow, but yeah, I mean, if what you think you're getting at the end of that is like something that will help you generalize to whatever it is you care to test on, right? So if the things you expect to test on are the output of 1,000 Adobe filters, then yeah, that's a great thing to do. If it's not, it may not be. And this goes back to like the original questions about when we talk about machine learning in general. It's about like what is the universe of the things that you're trying to model, the things that you're trying to predict. So like those kind of choices are determined by that. But yeah, totally. Any sort of transformation. In fact, I think my next slide is exactly that. There you're basically data augment like crazy. Go crazy. Lens distortion. That's a bit like what you were just suggesting. We didn't talk about rotations, but you could do rotations if it made sense. Stretching, shearing, and there's all kinds of things you could do. Just you have to just imagine, do these transformations actually help me generalize to what I expect to see in the tests? So, cool. Other questions? Okay. So yeah, heavy data augmentation. This by the way, this becomes like a regular practice from here on out for this competition and for like lots of networks. It wasn't like that they originated it, the idea. I mean, people were doing it, but it certainly made it popular. And you'll see as we go through this that like that whole thing of like predicting on 5 crops of the image. Like in a couple of years, they're predicting on like 144 crops of the image. I mean, it's a pretty useful technique. Okay, they also this is probably like one of the first successful uses, or like one of the first recognized uses of the technique of dropout. So what happens is you have a ton of parameters here, and you have it's very easy to overfit to your training set. Yeah.
With the augmentation, like how much did they scale up their input data? It's like tenfold, like increase when they augmented, or is it like a million times more? Like,
No, certainly not 9 times more. Yeah, let's see. Well, they did horizontal flips you count the croppings, and they did random croppings. I don't remember how many they did per trig, for example. But it's on the order of like 10 to 15 or something like that, which is huge because this is already like there's a million images in this. But yeah, it's certainly useful for generalization. Okay, so there's always a danger of overfitting to the training set, and when you have tons and tons of parameters, this becomes really easy to do. And so you kind of define against it, and that's what regularization is about. It's not fighting against that. So again, data augmentation is a regularization technique because it's using, so like the size of the network, the number of parameters is related to the capacity of the network to learn things. And what you want to avoid is just memorizing the training set. When you have tons of parameters, this becomes actually a problem. So you're trying to prevent that. So data augmentation does that by just giving it a whole bunch more examples that are they are correlated with the examples that they were created from, but they're not exactly the same image. So it doesn't, it's using up some of the capacity in the network to learn those, and so not just memorize the original training set. Another technique is dropout. Very, very useful, very effective. So dropout is exactly what it sounds like. Every time you run an iteration of like a forward pass, a backward pass for a mini batch, you actually randomly drop out neurons in each layer. Like you set the weight. Between any of these neurons to 0, so that they're not participating in the forward backward pass in training. So you literally drop them out. Yeah.
So does everything still get fully backpropagated?
It's fully backpropagated. It's just not. It just doesn't go through these neurons. So yeah, so it's done layer by layer. So you make sure that like there's still a pathway from input to output and back again.
Well, but what I mean is that like since you drop out those layers and you have no contribution.
We don't drop out the layers. We drop out the neurons.
I'm sorry, the neurons.
Yeah.
That's what I meant.
Okay.
When the gradients get propagated back through, they would still change the gradients for those neurons. Like,
Just the neurons that haven't been zeroed out. Yeah. So it's like you're masking out part of your network, and you're saying this part of the network is going to participate in the forward and backward pass in this iteration for this batch.
Once a neuron is dropped out for one forward pass, does it get reset in the next one?
Yep.
So
every pass, you get a different sample. Yep. Every single time. So and you choose a parameter. There's a hyperparameter here that says how many you're going to drop out. What percentage of them are you going to drop out? And in this, in AlexNet, they use a half. So basically, at every layer, half of the neurons are dropped out. There were a couple hands.
So if I do this dropout, is there a danger that I will omit neurons which were highly activated, meaning that there were features that I'm interested in and it's not contributing to my output?
Yeah, that is expected to happen. In fact, that's the reason for dropping them out.
And then when I reintroduce a neuron with their earlier weights being assigned, so how about the correction? How about the correction in that particular way? The neuron.
There's no correction. It just whatever the weight is at that point, that's what's used for the forward pass, and then what's used in the backward pass. It's just, it's like it didn't participate like in this iteration. It didn't participate now, but now it's going to participate. It's
so
like
if it's a random selection, then it may so happen that in few iterations that particular neuron doesn't get selected, and in that case the weight doesn't get updated. So we really don't have a chance to correct the weights. Because those neurons.
So like whatever, if it gets dropped out in an iteration, its weight is not going to be updated that iteration. But we're doing hundreds of thousands, millions of iterations, right? So it's going to participate in a ton of iterations, and its weights are going to get updated.
Yeah, so how does this help out in regularizing
Yeah, that's the next couple slides.
So when you do dropout, is it usually applied like layer by layer, like you would Just this, like you can drop out certain layers but not other layers.
You don't drop out layers.
Or
You drop out neurons from layers. If you're saying like, like are there some neurons that you would, or some layers you would protect from any dropout? I mean, you could do that. That's not the common way of doing it, but you could do that.
Does dropout like at the beginning have like a much bigger effect than like if you have a dropout layer, say later on?
I don't understand the question because you're always applying dropout to all the layers. You're always applying dropout. So it's just like it's like you have this network. You're like sampling a subnetwork of it, and it participates in a forward-backward pass. And then the next iteration, you sample another subnetwork, and it participates in a forward-backward pass. Other questions?
This is kind of, does that mean like theoretical rounding and like ensemble methods?
It's exactly an ensemble method. Okay, cool. So there's an implementation of it. Cool. It's not that it's really easy to do in NumPy, and guess what? We get to do it. So this is going back to whoever's question. I think it was your question about like you might have a really activated neuron. So yeah. So the point is that you don't. If there's a neuron that's really important for prediction, you don't want that to be the only neuron. Like that would be a very brittle network, right? What you're trying to do is you're trying to like distribute the importance of the features around the network, so that you're not relying on just one activation of just one neuron. So you don't get co-adaptation of features. It promotes like this redundant representation. And when it comes to ensembling, it's exactly ensembling. So this is the going interpretation of why this works so well. It's like an end-to-end ensembling method. So each time, so ensembling is this idea of I have one predictor and it does so well. Now I have another one, and I can just combine the predictions of both of them to usually give me predictions that are better than either one alone. And what an interpretation of dropout is that I have every time I'm sampling from I get a subnetwork. I'm sort of sampling from my original network. It's like that's one network participating in this ensemble of predictions in the end. It is just one network in the end. Like they're all at test time. All the neurons participate in making the prediction, but it's like a whole bunch of subnetworks are making them together at the same time.
What happens when you just disable dropout after you trained it really well? Does it go haywire? This is a curiosity question.
You're training along, and you've been using dropout, and then at like some point you just say, okay, no more dropout after these predictions. I know the answer. You should test that. That could be your project.
If you're trying to create redundancy, does that mean when you're using dropout, you should increase the number of neurons in each way?
No, because you're starting already with a huge network. Like you only do this when you have a network that has way more capacity than needed. So like, not every network does this. So like the ResNets that win the competition in 2015, they don't use dropout. They still have millions of parameters, but they have far less than AlexNet and VGGNet and things like that. So they don't need dropout to improve. There are other implicit forms of regularization in architecture that we'll get to, not today, but the next time. But you don't say like, oh, I'm going to apply dropout now, so let's increase the number of neurons. It's like what a typical thing you might do is you're training and you see that you're like way overfit, right? Like your training accuracy goes really high, but your validation accuracy, your test accuracy is really low. And you're like, okay, I have way too much capacity in this model, so let's try to regularize it. So now I add dropout. And usually you'll see the training accuracy come down and the validation accuracy, the test accuracy go up. Because you're no longer memorizing the training set. You're preventing it from memorizing the training set by effectively reducing the capacity. But dropout's a neat way of doing it because in the end you get an ensemble of smaller models that end up making the predictions. Yeah, there's some numbers here that are meant to blow your mind. Or whatever. The point being made here, you're not going to sample all the subnumbers. Okay, so the point about dropout, and there's a lot of regularization techniques that are like this, is that what's basically happening is we're making our output random. We're making a random variable. We're actually making it depend on some random variable. In this case, what's called z in this slide, but it's the mask. It's this mask that we decide to sample. It's saying like these neurons are active, these neurons are not. And at test time, what we want to do is we want to average out that randomness. Right? We use the randomness to regularize, but the randomness is like a bad thing at test time. We actually want to have the most accurate prediction we can make, and so we want to basically average out. We want to average over this ensemble of models that are parameterized by our random variable z. Yeah, but this integral seems hard, so often there's just like really simple ways to implement an approximate evaluation of that marginalization over z. So what happens in dropout is that if we just think about what's happening in a simple case, and you can convince yourself that it applies to the more general case, is that what we're trying to do is we're trying to do this average over the masks that, like the 4 masks that are available for these 2 neurons, right? Both on, both off, and then one on, one off, and then the other one on, and one off. There's 4 masks there. So, and they each get equal probability if we are sampling, if each neuron has a 0.5 probability of being chosen to be in the mask. So that means that each of those 4 combinations has a probability of 0.4, or 1 over 4, sorry, 0.25, so 0.5 times 0.5. And yeah, if you actually compute this average, then what you actually get is 1/2 of what the output we would typically get if we weren't doing dropout. So this is actually how we, at test time, sort of do this marginalization over the random sampling of the masks, is we just multiply by the dropout probability. So literally, at predict time, we just do our typical prediction, but we multiply by whatever the probability is. In this case, now it's at 0.5 of particular neuron in the set. That's nice. Like this is actually one of the reasons why Dropout's used a lot. Is not only does it sort of like have this nice interpretation in terms of ensembles, but like it's really easy to implement in the forward pass and backward pass, and it's really easy to implement at test time. Just multiply by it. In fact, yeah. So some code for what you would do to create this mask. Create the mask and do this entry-wise multiplication, and then multiply by p. But actually, what's typically done, what's more commonly done, is what's called inverted dropout. Is instead of doing the multiplication by p at test time, you actually do a division by p during training. So it gives you in the end the same effect. It's just you don't have to touch test time. You just don't touch what's happening in training. Just carries that p around, which is nice. Okay. Questions about dropout? Yeah.
So why do you have to scale it when you're actually doing your testing? Because since you're scaling all the neurons effectively equally, like, why does that matter? I don't follow.
You're not scaling all of them equally, right? You're actually dropping half of them out. There's not an equal scaling here.
Okay.
I don't know. Yeah, so let's see. If you go back to, let me see what I'm thinking about. different way to say that.
So P is constant, right?
Yes, P is constant.
So you're doing it for all. Then when you attest, so the previous slide you were like multiplying the prediction with P. And you're doing it for all. So I guess that's what you meant.
Yeah, that is.
At test time, you're multiplying by P, but not at training time. At training time, I mean, actually, in the inverted you are, you can divide by P, but that's just a convenience.
Yeah, I get how dropout works and like why it's useful. I don't see why it's necessary to at test time now compensate, right? To do the multiplication at test time, say, oh, we need to scale it by 1/2, right?
Okay, let me see. Your question is something like, shouldn't all the scores just scale the same way?
Yeah, exactly.
Let's see, let's go back to this picture right here. So, what you are saying is true if there were no nonlinearities. Yeah, the scores would just scale up appropriately if there were no nonlinearities in the neural network.
Okay.
But because of the nonlinearities, we don't get that doesn't happen we don't get this ordering of the scores as a result of having done that. That doesn't get preserved.
Okay.
And it's just a nice consequence of the discrete probabilities being used here that we get to multiply by this. So what's happening? Maybe I should point this out. Even more different from this out. So this is happening basically like at every layer you're multiplying by, like in test time you're multiplying by P. So so there's here's your ReLU. So here's your first layer, and here's your ReLU, and you're multiplying by P. And then that goes into this next nonlinearity.
That makes sense then. Yeah, that makes a lot of sense. If you're doing it by layer. Okay.
Yeah.
Thanks.
Okay, good question. Other questions? Again, this is a common way of thinking about regularization, is adding these, making your output depend on some sort of random variable. There's another technique we'll talk about next time called batch normalization, and it has this very same kind of property. Okay, cool. So coming back to AlexNet, this was definitely not an innovation. This is something that we really haven't talked about yet. So yeah, they had a batch size of 128. The SGD, so stochastic gradient descent, but with momentum. They had a momentum parameter of 0.9. So I want to talk about that for a second. So we talked about gradient descent and stochastic gradient descent. Gradient descent is gradient descent is using the gradient of the loss to adjust all the weights in your network, and doing this through discrete steps. And stochastic gradient descent is now we estimate that gradient with just a subsample of all of our data. So there are definitely problems with this. So, like for instance, this funny picture I have here, where this is what this is trying to do is show this loss function, where these regions up here, the loss is higher, and the regions within here that's lower. So we're trying to get in towards that not even really smiley face. So what happens is we really like to go straight towards it, but with stochastic gradient descent, if we have a direction in which the gradient's changing really slowly, and in other words, changing really rapidly, then we're going to do a lot of this hopping around each iteration. You know, like we're going to be here, we're going to say like, okay, I mean, I want to go this direction, so I'm going to have some component in that direction, but steep gradient in this direction, so when I jump across here, and then I calculate it kind of in reverse going back, and I do a lot of this jumping. But what I really want to do is kind of go straight towards it. And there's like a number of ways to think about that, and there's a number of techniques for dealing with it, and I'm going to go through a couple of them. Also, you know, we have this constant problem with our loss function that there's tons of local minima, and we haven't talked much about this, but there's also these things called saddle points. In fact, it turns out that there's really a ton of saddle points in neural network loss functions, and like a ton of cool research going on around that and why it is. But saddle points basically, it's a point where gradients are, at least in one direction, gradients is 0, but if you move in a particular direction, your gradient is going to become negative, and if you move in the other direction, the gradient is going to become positive. So it's like, it's not a minimum, it's not a maximum, it's something kind of in between. And you can get stuck there. We don't want to get stuck there. So like we could get really unlucky and just sort of like land right here and be like, have a 0 gradient and not move. And that would be bad. So we want to avoid that kind of stuff as well. Another problem is just sort of plain vanilla stochastic gradient descent. So how do we fix this? Well, a very common, very effective way to do this is to add momentum, what's called momentum, to stochastic gradient descent. So this is gradient descent as we've learned it. You calculate your gradient, you locally at where you are, you pick some sort of learning rate, in this case it's alpha, and you walk in the opposite direction of your gradient. That would be in the direction of greatest descent for that function, at least locally. So what SGV plus momentum does is it just sort of keeps around the gradients from previous iterations to help kind of, it keeps like around the memory of the gradients you've used in the past. So that, like, for instance, you can see this immediately solves this saddle point problem. If you get to a place where your gradient is 0, you will actually move. If you got there, you had from someplace else, you had a non-zero gradient in the step before. And if you keep around some of that gradient when calculating the next step, then you're going to move out of it. And the way that this is written is you could keep this, you could put this all into one equation, but it's kind of nice to see it broken up. Is that we have a parameter, so we have something very similar here in this update step for our weights. In this case, X, or it could be W. That looks like that, except for instead of putting the gradient there, we have this term v equals 1, and what is that? It's the gradient plus whatever v was the time previous times some parameter rho, which we take to be between 0 and 1. So it's decreasing the value of what was remembered from the time before and adding that to the gradient. Yeah?
It's not really obvious to me what the end condition is because we can't rely on the gradient being small anymore. Do we like check for oscillating directions or something? Like when do we know when to stop?
When to stop. When I don't understand your question. So you're saying like the gradient would always be large here or something?
No. If we get to a 0 gradient, we keep going because of momentum, right?
Yep.
So when do we know when we found a good minimum?
Yeah. So
wouldn't the momentum die out?
Yeah. So what you hope happens, and like the concern I think you're expressing does exist, is so you can see how like if you're at a saddle point, it just sort of gets you bumped off there because you have some gradient. But if you really are in some sort of local minimum, then what you hope is, well, let's say you actually ended up at the minimum of it, right? So the gradient you're actually contributing is 0, but there's some other gradient that would get you to move. What you hope is that you've chosen rho in such a way that this and your learning rate in such a way that the combination of those two, that when you move, you only move to say like here, you don't actually leave the well that you're in, but you move to here so that your next step brings you back down over here. And you can see that like once you're kind of like trapped like that, over time, because that row is less than 1, that eventually you are going to end up back over here. It's just going to take a few more steps to get there. And what could happen though is that this could be too shallow, like this could be too shallow or not wide enough. And yeah, like you could jump out of this and go on. I think that's kind of what you're expressing is like there is this potential to jump out of the local minimum. But if it really is like a global minimum, then you're going to come back here eventually anyways. And if it's not a global minimum, then you kind of want to jump out of it. But maybe it's a global minimum. And what happens is like you keep jumping out of it and jumping back into it, jumping out of it and jumping back in. And that would just be like a bad choice of row and learning rate. And you deal with that, as we'll talk about at some point, by like actually reducing the learning rate over time. This is another technique. Again, all great empirical stuff. Was there another question? First of all, did that answer your question?
Yeah, that exactly.
Cool. Other questions? Okay, so so all we do is we kind of keep around a memory, this exponentially decaying memory. So like the V2, the VT, as time progresses, the part that's contributing to VT plus N is proportional to the row to the nth power. So it's this exponential memory. It's decaying exponentially. And so eventually, those things are dying out, all of them. So this actually helps a ton, like a ton. And so to the point that no one ever trains with stochastic gradient descent alone. That would be like using a sigmoid. It would show you don't know anything. You would at least be training with sigmoid plus, a stochastic gradient descent plus momentum. It's really effective. And like the typical values for rho being 0.9 or 0.99. Again, it's a hyperparameter that if you care to tune it, you could tune it, but like a choice of 0.9 is very common. And Alex meant to use 0.9. And when I train with stochastic gradient descent momentum, I use 0.9 to start with. It's just a common choice. But again, it's usually you can tune it to be better than that, to get lower loss. But usually not much lower. It can be formulated in different ways. So this is formulated by actually making like the gradient descent step and putting that into memory, in which case you would just add the term v t plus 1 there. It's exactly the same, but you might see it implemented when they talk about differently, but they're equivalent. You can show that those two are equivalent. So it makes it so that instead of jumping around, we keep a memory of the direction that we're going, and it smooths out our pathway to our local minimum. There is one more related update rule like this that people use, but you don't see it much. You usually see stochastic gradient descent plus just momentum like we discussed, or you see another technique that we'll talk about in a while called atom. But there's something related to this called Nesterov momentum. So the actual step we take is a combination of like our memory of a gradient's past and our current gradient. And that's the actual step we take. There's another technique that actually says, it kind of looks ahead and it says, let's compute like a gradient. Let's imagine that we actually took the step in the direction of the velocity. And let's compute that gradient, and then let's use that to take an actual step. And it's sort of strange to think about doing that, but it's a technique that's used, it's effective, and it looks like this. So the momentum term, instead of keeping in this case you're subtracting, but like adding to it the gradient descent term at xt, you actually, literally like what I just said, you actually take the previous momentum, calculate the gradient there, and then use that to take your step.
And it seems really backwards, and even when I like was putting this together and looking at it, so like this still is so weird, but actually it works. It works fine. And usually people don't like to see the gradient like that. So what you do when you're using this technique is you make a change of variables. You just whatever that ugly thing is in there, you just call that x tilde, and then you can rewrite those rules like this. And yeah, then you're like maybe happier, I guess. I don't know. It's equivalent, just maybe a little bit happier. You still have to, when you do your update of your weights, you still need to calculate this guy. You don't update with that guy. But so yeah, you like look ahead and use that gradient, and that somehow gives you a really nice update rule. So here's a cool illustration of this. It actually has more than just SGD, momentum, and Nesterov. But NAG stands for Nesterov accelerated gradient. So there's also these other techniques that we're going to talk about, but I want to show this right now just to kind of give you a sense. So ignore the blue, yellow, and black traces. But what you're going to see is you're going to see, starting from that black dot. So here's our initial starting point. Here's our global, or sorry, not our global, well, it might be global, our local minimum that we're nearby. And what we're going to see is using these different rules and this loss surface here, we're going to see what each of them, what the trajectory of looks like. They all are using the same minimum rate. So ignore all those really, really good ones. I just went straight to the to the minimum. So SUD is like slowly coming out behind everybody else. Notice what momentum, SUD plus momentum, and then SUD plus Nesterov momentum did. They did something kind of weird, but they actually in the end got to the minimum faster. And I guess the point of showing you this is one, like it's an illustration of why you might consider using these other techniques over SGD just in this one particular case. But another thing is too, like it's not to believe that momentum or Nesterov momentum is like some amazing magical wand that would prevent you from doing weird things like this. But it's more principled in the sense that it will get you to your minimum faster. And it's, like I said, if you use plain vanilla SGD, you will show yourself to be a noob and not part of the code society. So you want to be in part of the code society. Now, what are those other things? Well, we'll talk about those later. Okay, so AlexNet, they use the starting learning rate of 0.01. And then what they did was they reduced it by a factor of 10 every time that the validation accuracy plateaued. This is a really common technique, so much so that basically like every deep learning framework that you pick up will have something for allowing you to set this up. And yeah, it works really well. So it's like, you have this loss surface with all this stuff going on. You sort of search in it at a certain loading rate for a while until you find some region in which you're sort of converging. And then once you've done that, then you drop the loading rate by a factor of 10. And that allows you to explore like narrower wells, like get down deeper to narrow wells, deeper wells. And then then like it's sort of rinse and repeat. Like you're now like exploring in there, this taking shorter steps. And when you sort of find that like a region where you're fills up your conversion, then you do that again, and you can get into even deeper, narrower wells by taking smaller steps. It's super common. Again, you better do something like this, or else people will think you're really good. And they did use some L2 regularization. So yeah, all these things put together allow them to train a pretty large convolutional network. At the time, it had 8 layers. At the time, it was like this massive revelation to the computer vision community that like these things could work. And mainly again because it just did so much better than the previous year. I already pointed this out about how like they actually split up the feature maps across multiple GPUs. This was their way of doing parallelization across multiple GPUs.
It turns out that like the COM1, COM2, COM4, COM5, the connections between those layers were just on the GPU. They didn't share. So no information from the other GPU. Like none of those feature maps were shared down below the computing the features in the next layer for those layers. And then I don't know how they chose this. It's not really explained. But then in the third convolutional layer and then the fully connected layers, those were actually those weights were shared. So it doesn't matter because no one trains like that, but it's sort of fun to know. So yeah, so the previous best top 5 test accuracy was 26.2. These guys came in and they had with just one of these networks, kind of using all the techniques that I just described, they got a validation accuracy or top 5 validation error of 18.2. But then they trained 5 different ones, and then they ensembled their predictions together. So just took again the soft maxes from all of those 5, averaged together, and used that for prediction. And they're able to lower the top 5 error rate down to 16.4, almost 2 percentage points. And this is like really common. Like ensembling almost always gets you 2 percentage points of reduction in error, or increase in accuracy. It's just like one of those things.
Is there an intuition behind what your function is going to look like based on your optimization? Roughly?
What your loss function is going to look like?
Yeah. So what you're optimizing?
No. No, I mean, like, these have millions and millions of parameters. Like, there's no single human being that can tell you anything about what's going on in those. Like, the best people can do is talk about, like, symmetries within this multi-million dimensional space. That's really, there's no way of doing it. Some people, like, try to visualize these things, like, taking 2 sets of parameters. Like, so you take 2, okay, so your network converges to 2 different sets of weights. And then what is often done is like, because it's kind of fun to see, I guess, is you like, okay, so you have like 10 million parameters here, or 100 million parameters here, and 100 million parameters here. And then you draw the line, you just do this linear interpolation between the 2, and you compute the loss at each of those interpolated points. And what you draw is all the things I'm drawing over here, right? So you're seeing like a one-dimensional slice of what this loss function looks like in 100 million dimensions. But yeah, sometimes that's done. Like there's some point to it, but it doesn't really help you to understand what's going on. Like what it can do is it can say like, you know, in between these 2 places. So I say it looks like pictures like this, but it really looks like there's pictures like this. So it's like it's we have minimum, you have another minimum, and what you can see is loss increases and decreases again. So like you draw this. This is 100 million dimensions or whatever it is, and you have this like one-dimensional slice in between them. So I don't know. Does that help you understand it? But it kind of gives you a good feeling, like, hey, I think I know what's going on here. It should be noted too that they did some additional. They were able to get it. They were able to with pre-training their networks on the previous year's released data. They were actually able to reduce their error rate even more. So arguing for pre-training. So yeah, they get 16.4. An error rate of 16.4. That was just a massive, massive revelation to the computer vision community that like these things were going to work. Yeah, question? No? No question? Okay. Well, our time's up, so we'll pick up this very interesting history lesson next time. Remember that as part of history we learned about dropout, we learned about SGD with momentum, and Nesterov, updates, and all kinds of great stuff. So don't forget to turn your homework in. Turn it in using Canvas.
I got it. Yeah, but